good.
All right, so let's get started. So hello everyone, thank you for being here with us first. Today we are going to present you our E4 project, which is called the MALIS project. Our team is composed of Quentin Garrido, Tiffany lamy-verdin, myself Raphaël Laperto, Jocelyn Lefebvre and Annie Lim. This project was supervised by Laurent Najman, who is present here with us. And a GitHub of our project is already available at this link, so you can check this out after this presentation. Now let's dive into it. Our project stems from the complete imaging of a Drosophila's connectome made last summer. The idea is to perform image segmentation on this fly brain imagery in order to extract an architecture of the brain, which would greatly help to understand how the brain works. And then in the future, if one day we have imaging of the human brain, we can do the same to better understand the human brain, which is pretty cool. So how do you go about segmenting an image? There are several approaches for image segmentation. There is a boundary detection and the semantic segmentation. There is also the object detection, but it's a bit different. Doing semantic segmentation consists of predicting for all pixels to which object belongs the pixel. For our problem, for instance, we predict for each pixel if it is the boundary of a cell or the interior of a cell. We tried this approach, but we quickly left it because the boundary detection approach was more accurate for our problem. Boundary detection consists of, well, detecting the boundaries between two objects. We'll go further into the details of this approach afterwards. As we don't want to detect objects, but separate them, we did not try the object detection approach. Let me do a quick summary of what this presentation is made of. We'll first introduce the method that we used, which is the MALIS approach. We will then see how did we implement it, and we will detail some advanced technique that we used. Afterwards, we will detail our results and how did we measure how good our results are. And we will finish this presentation with a quick overview of how we managed this project and what were the difficulties that we encountered. Okay, so now let's get right into it. So what is MALIS? MALIS stands for Maximin Affinity Learning of Image Segmentation. Overall, it consists of the following. You have an image that you want to segment. The first step is to predict for each pair of neighbor pixels their affinity. We will see how do we predict this affinity in the next slide. When we have this affinity grid, we first threshold the affinities. For example, if the affinity predicted between two pixels is below, let's say, 0.5, then these two pixels do not belong to the same object, and vice versa. After this thresholding, we also do some post-processing that we will detail afterwards. So now, to construct the affinity grid, there are several approaches. A simple method is to simply calculate the distance between the two pixels in terms of value. For example, if the first pixel has value 100 and the second 150, the distance between the two pixels will be 50, and then the higher the distance, the lower the affinity. Another method would be to use any kind of binary classifier that is smooth. In order to predict an affinity grid without thresholding directly, the binary classifier has to predict a probability, and not the classes themselves. As neural networks have proven themselves in computer vision, the MALIS approach uses them naturally. We first tried a simple convolutional neural network, and then upgraded to a more promising architecture, which is a U-Net. Now I'll let Jocelyn talk about how to measure the error of the models with the RAND index.
In order to predict these affinities, MALIS will optimize directly a measure of segmentation quality. This is really interesting since segmentation are always evaluated using these metrics. And here, the round index. The idea with the round index is to take each pairs of pixel in the image and check if they belong to the same segment for the ground truth and the projected image. Here on this video, we can see that we have three segments in our ground truth, the green one, red one, and purple one. And edges gave the segmentations, the segment for the projected image. So we can see that we have only two segments, one with the red and the green segment, and the second one with the purple segment. Round index use the indicator function, delta, that take in input 2 pixels of the image and output 1 if they belong to the same segment and 0 otherwise. Here we have picked 2 pixels. The first one belongs to the green segment and the second one belongs to the red. For ground truth, the indicator function will output 0, but we have a misclassifying edge, the dark one. This edge will merge two regions. So for our predicted image, the indicator function will output 0. If we were computing the loss by taking the difference between each edge for the predicted image and the ground truth, here we only have one misclassified edge. But with round index, this kind of edges this kind of misclassified edges will be heavily penalized by the round index because a whole segment will be considered as misclassified. This edge is called the maximum edge, and we will see how to get to compute the maximum affinity, the affinity of the maximum edge. We have two notions. The first one is the maximum path, a maximum path between two pixels I and J, and the path that maximizes the minimal affinity between these two pixels. The maximum affinity is the affinity of the maximum edge, the edge with the lowest affinity on the maximum path. In order to obtain this maximum affinity by obtaining the maximum path, we'll use the property that any path in a maximum spanning tree is a maximum path. Next slide, please. In the first version of MALIS paper, we're only picking a single pair of random pixel I and J and find the affinity between them to compute the loss. But it's too bad because we are computing the maximum spanning tree on the whole image for only use one edge. In the next slide, Quentin will detail the loss for the new MALIS paper that use way much more information from this maximum spanning tree.
So the MALIS method was improved in 2019 in the paper Large-Scale Image Segmentation with Structured Loss-Based Deep Learning for Connectome Segmentation here. The idea is that before we only picked one pair of edges, one pair of pixels, sorry. But we would like to compute the loss for every pair of pixels in an image. However, there are n squared pair of pixels in an image, which is a bit too prohibitive from a computation point of view. What we would want optimally would just be this. For every pair of pixels in an image, we compute the loss with still the function saying are the pixels u and v in the same object, and the affinity of the maximum edge. This is not usable in practice, but there is a trick that is used to reduce this to a quasi-linear computation, so in a big O of n log n. The idea is that we know that every maximum edge is an edge in the maximum spanning tree, and vice versa, every edge in the maximum spanning tree is a maximum edge. So we only need to care about those edges. We will define the two weights, the positive weights Wp and the negative weights Wn, that are defined as follow. The positive weight of an edge is for every edge in the maximum spanning tree, how many pixels that belong to the same object have this edge as the maximum edge. And the negative weight is is almost the same, but it's for every edge in the maximum spanning tree. For how many pairs of pixels is it a negative edge? So an edge between objects. This leads to this formulation of the loss function, which only has to sum over all the edges in the maximum spanning tree. So we have only n edges for the sum instead of n squared pair of pixels, which is already great. However, there's one issue. How can we compute WP and WN easily? The idea is to compute them on the fly when computing the maximum spanning tree using the Kruskal algorithm. Whenever we are adding an edge to our maximum spanning tree, we merge two trees T1 and T2. So we will define VT1 VT of I, which is the set of all pixels in the tree T1 with the class I. And the same goes for VT2 VT2 of I, the vertices in the tree T2 with class I. So as such, the positive weight, we know that when we are adding an edge to the maximum spanning tree that fuses two trees, if we take one pixel in T1 and one pixel in T2, this edge will be the maximum edge for this pair, because it's the minimum value that link them together. And since afterwards, when we are adding other edges to the maximum spanning tree, they will have a lower value. We know that this one is the maximum edge for this pair of points. As such, to compute WP, we only need to sum for every class the area of pixels with label I in the tree T1 times the number of pixels with label I in T2. We multiply them together because if we have n pair of pixels, we just need to multiply them together to get all the possible combinations. As for every pixel in T1 with label I, we can find this number of pixels in T2 with label I. And then we can do the same with Wn. That is the same definition, except that here we want I and j with j different than I, which is a bit harder to compute, but we can easily rearrange it to compute as just all the total pair of points in both trees minus the positive weight. That will give us the negative weight. And so we can compute this on the fly when constructing the maximum spanning tree that we have to do anyway, with only a small additional cost with a factor k. So instead of being in n log n, we will be in k n log n. But since k is way smaller than n in practice, since n is the number of pixels, this is almost negligible.
To resume our method, the method used in the original MALIS paper, after getting our affinity graph, we remove the graph's edges by thresholding it. It will give us the connected components corresponding to objects in our image.
Cool.
We can use additional post-processing to have better results, like watershed. And we can also use watershed and then merge small regions into bigger ones. We can use a MUN for char and then do a graph cut. We also try to do a watershed and agglomeration, as mentioned in the second paper in the improved MALIS. So I will explain a bit what is the agglomeration. So we compute a region adjacency graph. The nodes represent the objects, and the edges value the affinity between the objects. The nodes with lowest edge value are merged together, and we repeat this process until the edges value are higher than the set value that we choose. Now that we presented the MALIS method, we are going to show you our implementation.
Now that you know how our method works, we'll see how we did our implementation. Since the image is too big to compute the loss over its entirety, we'll feed it smaller patches in the input of our network. We will feed our network our image patch and get as outputs the edge weights in direction x, y, and z, or just x and y in our case. We'll then use those edge weights to generate our affinity graph that will be used to compute the loss. PyTorch library was used for the neural network, and we use the HIGRA library to compute the loss and the post-processing.
We need some information to compute the loss, and we can have this information by using a binary partition tree, a tree built by altitude ordering using the Kruskal algorithm. So this tree has the data of a maximum spanning tree. And you can see on the figure here how does this tree is built. Why do we have to use this? Because it's very easy to pick the maximum edge, because the maximum edge between two pixels I and J is the lowest common ancestor of the two pixels in this binary partition tree. Quentin was talking earlier about WP and WN, and to compute these two terms, we have to use the area of edge. And by building a binary partition tree using IGRA, we can access very quickly to this information. Here we have a pretty little animation to explain how does this binary partition tree is built on a 2D image.
So as we have seen, we can use the binary partition tree to efficiently compute the loss, but still it's not perfect. As we can see in the loss function, for every edge in the maximum spanning tree, we have both a positive and negative weight. Every edge will have a non-zero value for those weights if the segmentation that we produce is not perfect, which is always the case in practice. However, even if we have an edge between objects like this one, we do not want to have its weight and compare and then compute the loss with the value 1, so the desired value, since the desired value will be 0, which doesn't make sense in practice to try to make it have value 1. So instead, the loss will be computed in two passes. So first, the goal of the first pass, the positive pass, is to compute the loss for all the weights, all the edges in an object, for example, these ones. The idea is that we will set all edges between objects with a value 0. What this does is that it makes the positive weight for such edges be 0, so we solve this problem, and then their loss will be 0 here, since they have value 0 in this case. So we only look at positive edges, so edges in the same objects, and their positive weights and negative weights, which is exactly what we want. And then in the second pass, we do the negative pass. We have to do it in two passes since when changing the value of the edge weights, we change completely the maximum spanning tree that we can see here in dark gray. Since it's completely different, we have to do it all over again to get a good result. So for the negative pass, we will set all edges in same objects to a value 1, and then compute the loss. This solves the same issue, as now all weights that are all edges that are positive edges will have value 1, so the loss will be 0, and we only care about the contribution then about our negative edges. And so we only take into account the terms in the loss that matters to us, and not the ones that would cause some erroneous behavior. And then once we have done those two passes, we just sum the losses and compute do the backpropagation using this sum of loss.
We talked about our implementation. Now let's dive right into our results. To produce them, we used a pretty simple unit architecture that you can see here. Blue arrows correspond to two convolutions without padding, which had better results in practice. Orange arrows going down correspond to downsampling with a max pooling. Yellow arrows going up correspond to a bilinear upsample plus a convolution. And red arrows correspond to crop plus a concatenation. And this figure, as you can see, is in 3D, 3 dimensions, but we made it in 2D in order to save time. In 3D, it would have been too time expensive for us. Now I'll let Jocelyn talk about the post-processing that we used.
Here we are. We have two outputs from our neural networks. The first one is the affinity following the axis Y, and the second one following the axis X. The first step is to merge these two images by taking for each edge the mean of the
Hello?
Then on this image, we will perform watershed algorithm to obtain our final segmentation. Watershed was gave us the better results. We were trying other algorithms such as mem4sha, but for one single image, it takes more than 2 or 3 minutes. Theoretically, we have to work on 3 images, so it's not possible. And at the same time, Watershed performed very well in just a few seconds. Now we'll focus on the parameter threshold, theta. In the previous slide, we're using theta of 0.25. Here we don't have a problem of oral segmentation. For example, with the third image, we have a very high theta. There is still remaining a lot of information. And by applying the watershed algorithm, we could have another segmentation. At contrary, if theta is too low, you can have segments that are under segmentation. By tweaking this the parameter theta, we can adjust the level of segmentation.
An issue that we can see between those results is that we have an affinity along the x-axis and the y-axis that is really different. In one case, we have almost a white everywhere, so affinity 1 everywhere, which is what we expect. And in the other case, we have almost a black everywhere except on the borders and on certain objects that are not present in the other. Sometimes it was the x-axis that was all dark, sometimes it was the y-axis, sometimes neither of them, but most of the time it was one of them. This issue this can be problematic when we are doing when we are calculating the mean of both affinities and thresholding afterwards, as this causes an image that is a bit erroneous in a sense, as we would expect them to be almost similar. At a small scale, the affinities along the x and y axis should be quite different, but on such a scale of an image with almost or more than 1 million pixels, there should be almost no difference visible. With this problem comes from the fact that we can have multiple different graphs with the same MALIS loss. So on the right side here, we have our scenario. Here, all the edges along the y-axis have a value 0 for the affinity, but except on the border, and the edges on the y and the x-axis have all value 1. And on the left, we have the same, but with value 1 everywhere. Both of them produce the same maximum spanning tree, can produce the same maximum spanning tree, but are really different in practice. But since both of them have the same loss, there's no incentive for a neural network to learn one instead of the other. Although we would prefer this one in practice, this one, the right one, is just as valid as it gives us the same loss. We don't know if this issue was also present in the paper, as it was not talked about. But our first guess is that it comes a bit to a kind of a luck, as sometimes it didn't appear at first, but then it changed after a few thousand iterations and then turned into this scenario. And another possibility is that when we are computing the maximum spanning tree, when we have multiple edges that have the same value, which is the case when we are setting all of the negative edges to 0 or the positive edges to 1, then we will pick the first one, which can lead to what we believe to be such behavior, but we're not sure of the reason why exactly. We didn't have time to investigate this behavior. But still, we could alleviate this issue by enforcing a loss on the loss that we didn't want to use at first, which is that comparing edge value by edge value, could be used in complement to this MALIS loss to alleviate such issues and force those edges to take the right value, which is 1 instead of 0. This could also give us better results afterwards in our when we are doing the post-processing, as we would have when we are doing the mean and the threshold. We would have more similar looking graphs and more plausible looking graphs than what we have currently. So now that we have seen how did we predict our image for the results, we are going to look at the dataset where we evaluated them, which is the CREMI dataset.
So we evaluated our method on the CREMI dataset, just like Antal said, which is composed of Drosophila brain images. Only one volume was used for the training, which has a size of 1250 by 1250 by 125. We evaluated with the code suggested with the dataset using a Python 2 library. We had to adapt it in Python 3. To get an even bigger dataset for the training, we used data augmentation with the elastic modification of the brightness and contrast, and also vertical and a horizontal flip, just like in the paper. As you can see in the image, there are quite thin edges and strong nucleus, which can add difficulty to do our segmentation. We'll try to get closer to the ground truth as much as possible. Unfortunately, we couldn't create an account to submit our predictions, so we had to split the available images for training and testing. As it was said, we're not predicting in 3D, so we'll take 125 images of size 1250 by 1250. We'll split the dataset in 100 images for the training and 25 images for the testing. Here is an example of our segmentation on one image of our test set. We can compare our segmentation with the ground truth and see how similar it is. As you can see, the different objects are pretty well segmented. However, this is not easy to compare, so we will draw the contours on the original image for visualization purposes. We have here, for the same image, the contours of the different objects. By comparing our segmentation, we can see that we are rather close to the ground truth, and most cells are well segmented. Even the nucleus we're taking into account in the segmentation, which is what we want. However, there are still some missing boundaries, which cause the fusion of two cells. For example, here at the bottom of our segmentation, the two cells are fused since a boundary is missing. We evaluated our results with several metrics. First, the round index, as we talked earlier, which should be closer to 1 to be better. Also, the variation of information, the VOI merge and split. The variation of information is defined as the VOI of X and Y equal to the conditional entropy of X knowing Y plus the conditional entropy of Y knowing X. If Y is a ground truth segmentation, then the VY merge can be interpreted as the amount of under-segmentation of Y, and the VY split is then the amount of over-segmentation. In other words, a perfect over-segmentation, we have the VOI merge equal to 0, and a perfect under-segmentation, we have the VOI split equal to 0. The split should be lower to be better. The VOI should be lower to be better. Okay, sorry. And the Crumis score, which corresponds to the geometric mean of the VOI, and 1 minus the round index. It was the score to rank our submission to the leaderboard. It also should be lower to be better. Here are our numerical results on the training set. The fully convolutional network plus MALIS loss is what we obtain after implementing the first paper. The unit is just a unit with a binary cross-entropy loss. Finally, the unit MALA is a unit with a constrained MALIS loss. Both this and the unit had the same post-processing. For the training set, we get the round index of 0.83 for the unit MALA, which is much higher than the simple unit with a round index of 0.58, and also higher than the round index of 0.61 we get with the FCN. The unit MALA have the lowest VOI merge by far, while the FCN have the highest. The VOI split are quite the same for the unit and unit MALA. However, it's good to note that there's a trade-off between the VOI merge and VOI split. And as such, comparison sum is a better indicator. Our unit MALA has the best Crumis score of 0.42 compared to the simple unit and the FCN. We can see that our unit MALA has the best result on the training set, and we'll see if it's also the case on the train set. Just like the training set, here are our numerical results for the test set. As we can see, the results with the unit MALA are quite similar to what we had before, thanks in part to the data augmentation that allows it to be more robust. As before, our Crumis score is much lower when compared to the unit, which is to be expected and a good indicator of success. However, as you can see, we're still far from the state of the art, especially for the VOI. One thing that could cause this is the different post-processing used. We didn't have time to implement perfectly the post-processing used in the paper and used a simpler one. However, we can't really compare our results with the state of the art because it's in 3D and we're predicting in 2D, which causes us to use less information when predicting. Yet we still have very good results that demonstrate the benefits of the MALIS loss.
We are now going to talk about the project organization. So same as we did during the first semester, we continue to use Trello as a tool to organize ourselves. We make weekly reports and weekly meetings to talk about our progress or potential difficulties. Since the beginning of the quarantine, we make all our meetings with Hangouts by alternating the meeting host. We also use more social networks to communicate with the team members, like Discord, allowing us to talk to each other, Slack and Messenger to share information related to the project. Overall, this project was not very easy. As we said during the first presentation, our first challenge was the reading and the understanding of the scientific papers. For some of us, it was the first time that we read one, so we weren't used to read the technical articles in English. But to overcome this, we planned a meeting in which we discussed the paper and what was important to understand in the papers. At first, we also had a lack of basic knowledge on mathematical morphology or image processing, so it took us some time before having a good understanding. During the project, we used the Higra library and PyTorch. Those two things were new, so we had to learn how to use them. PyTorch has a tutorial giving an example of how to create a simple neural network, so it was quite intuitive how to use it. However, Higra was a bit more complicated, as at first we did not know what exactly we should use for the implementation. We could not easily find the Higra functions needed. But once we knew, we just needed to find and use this specific function. Examples were also given in commented netbooks, which helped us a lot. The one main big difference that we had compared to the first semester is the quarantine. Because of this, we could not meet with each other and work in a proper environment. First, because of the internet connection, we also may not have good computers with enough RAM to run some codes on Jupyter notebooks. But that aside, we managed to adapt to the situation. We continue to get in touch with each other by using social networks, like I said earlier, and continue working on our project. So we managed to have better results than the ones we got in the first semester. This is due to the implementation that we made, like the UNet, the computation of the new loss, and the post-processing. After those 8 months of work on this project, we are happy to get these results. It was not easy and sometimes frustrating, but we managed to get there. Despite that, we had a lot of fun working on this project, and there are many interesting things we were about to work on. It was really pleasant to work together as a team, as we get along well and could do a lot of things. This project was really challenging, but this is what made it very exciting. It feels like we grew up doing this project as we learned a lot of things. So we would like to thank Mr. Najman for supervising us all along and giving us the opportunity to work on this project. Thank you for listening to our presentation, and if you have any questions, feel free to ask them.
So thank you very much for this nice presentation.